Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. So in this session, we are going to discussing about the phasor representation of the sinusoidal waveform. In the last session, we have discussed about the fundamentals in AC circuits and also the introduction to the sinusoidal waveform. So in that, we have discussed about the instantaneous value and also the magnitude of the signal and also the amplitude value and time period of the alternating quantity and also the frequency of the signal. There's so many things we have discussed it. After that, we have also done about the introduction to sinusoidal waveform. So that means how can we get the sinusoidal waveform, and what does it mean by RMS value, and what does it mean by average value, and also the peak factor of the sinusoidal waveform, and also the form factor of the sinusoidal waveform. So there's so many things we have covered in the last session. So in this session, we are going to discussing about the phasor representation of the sinusoidal waveform. So the overview of the session means need to discuss about the phasor representation of the sinusoidal waveform, and after that we need to discuss about the different powers in AC circuits. And here in AC circuits we have the three kinds of power considered, that is real and reactive and also the apparent power. So we need to discuss a lot about this in this session. And after that we need to go for the power factor and also the importance of the power factor. So we will like to discuss in this session. So before going to involving into the phasor representation, first of all we need to discuss about the phasor. Phasor means it is a rotating vector. So before going to dealing about the phasor, that is a vector first. Vector means it's a quantity of an object which has the magnitude and direction. That's called vector. It is a quantity of an object. So it has it possesses the magnitude and also the angle. That's called vector. So we know the vector. Also we can say the vector nothing but it is a simple line with a head arrow. That's also called a vector. It is a vector. So vector means it is a simple line with a head arrow. That's called vector. So if you are able to rotate this vector, in any kind of plane like a complex plane or general plane, so we will consider as that one phasor. The phasor is simply nothing but it is a the rotating vector with some angle in the counterclockwise direction. That's called simply phasor. So vector rotation always considered in the counterclockwise direction only in the complex plane, so that we need to rotate the vector in the complex plane with the counterclockwise direction, anti-clockwise direction like this. So we need to rotate. So that's called simply phasor. So phasor means simply it is a rotating vector in the complex plane with the counterclockwise direction. That's simply called phasor. So now we need to deal about the phasor representation. So let us take a complex plane. This complex plane, so we are going to say it is a S equal to J sigma plus J omega. So this is called imaginary axis of the complex plane, and also this one is a real axis of the complex plane. So it has a two different real axis and also the two different imaginary axis. So this one is, we can say it is a positive real axis. So this one is, so we can say it's a negative real axis. It is a negative real axis. So this one is positive imaginary axis. Positive imaginary axis. This one we can consider as that is a negative real axis. This entire thing is we have to confirm as it is a complex plane. This one is whole thing is a complex plane. So I'm going to take a vector. So that is keep in the complex plane. So this is a vector. This is a vector. OA I'm going to take. So in this complex plane, for this vector, we have the two components. One is a y-axis component, other one is a x-axis component. So it was projected on, it was placed on the only the y-axis, so that there is no, there is no component of the y-axis. So here in this vector we have the two components, that is y-axis component, y-axis value, also we can say imaginary axis value and as well as real axis value. So here I am going to representing the imaginary axis value on this plane. Separately I am going to project the imaginary axis value on this plane, and the real axis value I am going to representing in this plane. So this plane I am going to keeping the imaginary axis values or imaginary component values. Imaginary component values on this plane. So that is simply say y-axis component values. Imaginary axis values or y-axis component value. The projection of the vector, the projection of this vector, that is a x and y-axis component values in these two planes. So this one represents the real axis component value. So it is a real axis component value. So real axis also we can say it is a x-axis component value. Real axis or x-axis component value. real axis or x-axis component value. So first we need to consider the first instant. So this is a vector OA. So in this instant, so there is only a real axis component value. So that we need to project here. I mean, we need to project the real axis component value here. So this is the real axis component value. This is the instant A. So in this instant, there is no imaginary axis value. So that we need to keep, we need to project the same value in the imaginary plane. This is, so a point A. So then after that, I'm going to I'm going to rotate this vector. So if I are able to rotate this vector in the complex plane, that would like to represent or form the sinusoidal waveform. How we are going to get like this means we can see here. So we need to take one instant of the vector rotation. So this is the instant number 2. This is the instant number 1. So at this instant, the vector should be in this position. So there will be a real axis and also the imaginary axis component. So need to project the imaginary axis component value here. So we need to project the here our imaginary axis value component value here, and there will be a starting of the imaginary axis component value here. We need to project here. Then x axis component we need to project here. So this is the x-axis component value. So this is the x-axis component value. So in this instant, the vector B, so vector B we need to rotate, vector OA we need to rotate with some angle. So this is the theta. So that this one also we can consider as theta, and it is also theta. We need to rotate the vector with some angle, so that angle should be considered as the theta. So if you are able to fix that angle with like some value that is either 30 degrees or 40 degrees, 45 degrees or 60 degrees, like that, we need to rotate the vector in the complex plane. So I'm going to represent this vector. This vector angle should be, let us say, theta or either 30 degrees, let us say. So in this 30 degrees instant, we have the imaginary component value and also our imaginary axis value and also the real axis value. So the imaginary axis values are project on this plane, and also the real axis component value project on this plane. So this is the point B, and this is the point B. The next position we need to rotate, keep on continuing the rotation. So this is the point C. So this is the point C. So there is a projection of imaginary axis. So this is the point C. Then the real axis component value should be this one, the point C. So then keep on continuing the rotation, then we will get the one more instant. So that is a point D here. We need to rotate the vector from point A to B and also C and also D. So in this instant only we have the imaginary axis component value. There is no real axis component value, so that we need to keep the real axis component value should be 0 here. So there is no real axis component value. Only we will have the imaginary component value that will project on the this plane. So this is the imaginary axis component value. So then this is the point D. Then after that we need to keep on continue the rotation. So this is the point E. The instant number other one, that is a E. So then we need to project this imaginary axis component value. So that is on this plane. So that is instant number E it is. Then the real axis component value we need to keep here. So that is this one. So this is the real axis component value as a E it is. This is instant E, this is instant D. Then after that we need to continue the rotation of the vector in the complex plane with the counterclockwise direction. So this is the other one. So that is F it is, F instant. So need to project the real axis component value on this plane and the imaginary component value on this plane. So this is the real axis component value. So then the E is this one. Sorry, F is the instant number F is this one, and here also F is this one. So next after that we need to keep on continue the rotation of the vector. So then we will get this instant, that is the instant number G here. So we need to project this so this corresponding instant on the imaginary axis and also the real axis. So the imaginary axis should be like this. So it is the imaginary axis component value, that is a G here, and at this instant only we have the real axis component. So that is a high magnitude we got. So this is the real axis component value. So this is instant number G. So then keep on continue the rotation. So we will get this instant. So that is the instant number H it is. Then need to project the again real axis component value and also the imaginary axis component value. So this is the imaginary axis component value. Now this one is the So real axis component value. So this is the real axis component value, that is h it is. Then this one is, other instant we need to consider. So that is I instant. We need to keep the rotation in this plane should be counterclockwise direction. Then we need to consider the other instant, that is a instant number so that is 9 it is. Then at this instant there will be a y-axis and also the x-axis component values. So at this point, so this is the value of y, so this is h instant. Then other instant, the vector rotation we need to consider the equal angle, that's 30, 60, 90, like that. Again 30, 60, 90. So we need to take like that. So then we will get this instant as a, so this is a j instant. So then we need to project these values. So this is the instant number. So that is a j we can consider. So here the instant number j. So we need to consider as a instant number j here. The real axis component of the vector in this instant is a j here and j here, and the real imaginary axis component of the same vector should be j here. So then after that we need to consider as the instant number others. So that is, so this is instant number k. Then now we need to project the same vector. So this is k instant. Then after that, so the instant number others, that is a l instant. So we can consider this instant as l. Then after that, again vector comes to the same original position. So that is, this point is m, we can consider either a or m. So this is the m instant. So same also we need to keep here. After this one we got it as a I here. After the h we can consider as here I. Then after that we can take it as a j here. This one is a j. This one is a j. After the complete rotation of the vector in the complex plane, so we would like to get this kind of projections like imaginary and also the real axis components. If you are able to join these points, then we will get the pure sinusoidal waveform. The vector rotation in the complex plane should be represent the pure sinusoidal waveform. So here also we need to join this one. So we will get this as, so that is a shifted sinusoidal waveform we got. It is a shifted sinusoidal waveform. So this, if the vector is rotating in the complex plane with the counterclockwise direction, there will be a two component values. There will be a two axis value, that is a imaginary and also the real axis component value. So the imaginary axis component values, the imaginary axis projection will be mentioned here, and also the real axis component value we would like to mention here. So based on that we will get the formation of sinusoidal waveform. So this one is sinusoidal waveform. To say the vector rotation, under the vector rotation, the imaginary component of the vector rotation should form the sinusoidal waveform. This is a sinusoidal waveform. So in the vector rotation, the real axis component of the vector rotation should give the, so that is a cosine waveform. It is a cosine or shifted sine waveform. Shifted or cosine waveform. So this is the sinusoidal and also the cosine wave. So based on this one, we need to conclude. So the y-axis projection should be the formation of the sinusoidal waveform, and the x-axis projection should be formation of the cosine waveform. The standard and generalized form of the sinusoidal waveform should be, if it is considered as a x signal, then x of t equal to, it is a xm sine omega t. So this one. So this is the sinusoidal waveform standard notation. How can we write this? Means again it's the same. There's the same signal as a again x it is. So the corresponding signal should be, we can represent as x of t equal to, it is xm then cos of omega t plus or minus alpha. So for this we need to consider this one. So here we need to take the theta, means here we will get the theta only. Here also theta, then so this case also we can consider as a theta. So this is the phasor representation of the sinusoidal waveform. If you are able to rotate the vector in the complex plane, that would like to form the sinusoidal and also the cosine waveform. So this is the cosine waveform, and also this one is the sinusoidal waveform. So sinusoidal waveform doesn't mean that only sine wave, it's also a cosine and as well as the shifted sine waveform. So that will give the shifted sine wave also. So this is the phasor representation of the sinusoidal waveform. So here we also see the same thing in the animation. So if you are able to rotate the vector in the complex plane, so that would like to develop the sinusoidal waveform. So here also we have considered a different instance. Here they have, we have considered as a 45 degrees. So by the 45 degrees the rotation in the complex plane, we would like to get the complex, the formation of the sinusoidal waveform. So here we have considered as a y-axis component value, that is imaginary axis component value. So that is sinusoidal waveform. The rotation of the vector in the complex plane should form or representing the sinusoidal waveform. So this value we would like to write v equal to, that is a Vm sin omega t, this one. So this is a standard notation of this sinusoidal waveform. So this is the phasor representation of the simply sinusoidal waveform. So after that we need to discuss about the different leading and lagging concepts of the different alternating quantities. So let us take this instant. So this is the instant number 1. So if it is a resistive load, these things are going to happen in the resistive load, pure resistive loads only. So this is the, let us say the red one is a V, the red one is a voltage, and this one is the black one is a current. So it is a voltage and the current. So if you are able to draw the phasor representation of this one, means need to take the voltage as a reference. Voltage as a reference. So with reference to the voltage, the current should be always same phase with respect to the voltage. So this is the graphical notation of this alternating quantities. If you are able to keep this representation in the phasor diagram, so that will take it as, that will give it as this one only. That is, so this is a phasor notation of this, the same signal, same two alternating quantities. So with reference to the voltage phasor or voltage vector, then the current should be in phase. So that both are, V and Is are in phase. That is the voltage and currents are the same phase. So this is the voltage and currents of this corresponding instant. Another instant we can consider this is the voltage and this one is a current. So there will be a phase shift between these two. Phase shift means it's the angular displacement between the two alternating quantities. That's called phase shift or phase angle. So this is a pi, we can say. So the exact angle should be, this is a 0 and this one is a pi and this is a 2 pi, red one. So in this instant the current is always starts after the 90 degrees of the voltage. So hence we need to draw the phasor diagram of this one. So need to consider the V as a reference, voltage as a reference. So with reference to the voltage, the current is always lags behind the voltage at an angle of 90 degrees. So these things are going to get into the pure inductive loads. If it is an inductive load in the network, then we will get the phasor representation between the voltage and current should be like this. So this is the way of drawing the phasor diagram of this instant. So this is the first instant and the second this one, then this one is the third instant. Then I need to consider the other thing. If it is a capacitive load in the network, then the voltage should be applied. So like this, this is the voltage and this is the current. The black one is current and the red one is voltage. Based on this one, need to draw the phasor diagram. So how we are going to draw the phasor diagram means need to consider the voltage as a reference. So with reference to the voltage, the current is always leads the voltage. So the current of this alternating quantities always leads ahead the voltage at an angle of 90 degrees. So this kind of phasor representation we will get into the pure capacitive loads. So this is the phasor diagram of the pure capacitive load. So this is the leading and lagging concept of the different alternating quantities. So both are, in this case, both are in phase. Voltage and currents are the same phase. So there is no phase delay and also there is no phase shift. So based on that one, we will get the phasor diagram should be like this. Yeah, this one is a pure inductive case. The voltage and currents should be lagging. I mean to say the voltage always present the domination on the current, so that we can conclude. So the current of this system or this kind of circuit, the current is always lags the voltage at an angle of 90 degrees. In this case, so the voltage as a reference. In this case, the voltage as a reference, the current always leads ahead the voltage at an angle of 90 degrees. So this is the different instance to draw the phasor diagrams. So this R load, we'll get this. These things are into the R load, and these are into the L load, and these are into the pure capacitive loads. So the next concept of this session, that is power and power factor. So we already gone through the power in the DC circuit. So that is it's a product of the power always means it is electrical power only. So the electrical power is nothing but it is a product of the applied voltage and the current. So based on that one, so we have the categorized the different powers in the electrical system. So that is active power, or we can say real power, and other one is the reactive power, the other one, last one is apparent power. In any AC system, so whatever the loads are, utilize the power properly to produce the proper work, like producing the heat and also the lighting up the bulb and also the rotating the fan or mechanical functioning. So that kind of power is simply called real power. So this is also called as active power or useful power. Active or useful power. Useful power, that is useful power. In every AC system, we need to consider the three different powers, that is a real power, reactive power, apparent power. So whatever the loads are, utilize the power properly to produce the proper work. So that is the producing the heat and lighting up the bulb and doing the mechanical functioning or any motion. So that's called simply real and active power, real or active power. So it is always denoted by the capital P. Then we need to write the P equal to, so it is a voltage into, so that is active component of current, voltage into active component of, it is a current, then that is a V into I cos pi. Therefore P equal to, we need to write the notation of the active power should be P equal to cos pi, Vi cos pi, where the cos pi should be power factor of the system. It is a power factor of the system. So these things we will cover in the next slide. So that is a power factor. The units of this one is watts, or we can say kilowatt, or we can say megawatt. These are the units of active power. So this is active power. Active power, nothing but it is a useful or working power. So which you use it to perform the proper work, like which you use it to perform the work like producing the heat and also lighting up the bulb and as well as doing any kind of mechanical functioning. That's called real or active power. So that is equal to P equal to Vi cos pi. Then coming to the reactive power, so it simply say it is a non-working power. It's also called non-working power. So other words also we can say this one is, it is a useless power. Useless power. This kind of power is doesn't produce any kind of heat, like any kind of work. So this kind of power so cannot produce any kind of work or cannot do any kind of work. So that means so it doesn't give any lighting of the bulb and also any motion of the mechanical motion of the fan or like mechanical functioning. So due to that, so this one is called as reactive or non-working power. So reactive power means it's simply useless or non-working power. So which use it to consume the different elements in the network. So but the except the in the entire system, only the capacitor and inductor should consume this power to produce the some kind of useful power, like useful energy, that is a magnetic and electrostatic field. So the remaining all elements doesn't consume this power, doesn't produce any kind of work with the help of reactive power. That's simply called non-working or useless power. So reactive power simply called the non-working or useless power. So which doesn't produce any kind of work, only the inductor and capacitors consume this power to produce the required energies like electrostatic field and also the electromagnetic field. So that is the reactive power. So it is always denoted by capital Q. So that means voltage into, so that is a reactive component of voltage into reactive component of current. So reactive component of current. So which means V into I sin pi. Reactive component means we can consider as I sin pi. So therefore VQ equal to Vi sin pi. So the units of this one is, voltage is the volts, then current is the ampere. The units of this one is a volt ampere. If in case of a large scale, kVA, reactive component means it's a kVAR, reactive kVAR, or also we can measure this one is in terms of MVAR, megavolt ampere reactive. The units of this one is volt ampere reactive or kilovolt ampere reactive or megavolt ampere reactive. So this is regarding the non-working or reactive power. The last one is apparent power. It is also called complex power or total power of any system. So that is represented by the capital S. S equal to, so P plus JQ we can represent. So both are the vectors, so that we can represent the P plus JQ form. So if you are able to find the magnitude of this one, that is capital S equal to square root of, so P square plus Q square So P value we already know that is a Vi cos pi whole square. So then the next one is Vi sin pi. So that is also whole square we got. Then square root. So Vi comes out. Then a square root of sin square pi plus cos square pi. So this term we will get it as a 1. So then S equal to Vi. So the notation of apparent or complex power should be S equal to Vi. The units of this one is, so the unit of voltage is the volt, and the unit of current is the ampere. Volt ampere or kilovolt ampere, or the last one is megavolt ampere. So these are the different powers in electrical system: real power, useful power, the reactive power, useless power, non-working power. The last one is apparent power. So there are the different powers in electrical system: real power, reactive power, and apparent power. So that's all for today's session, and we will continue in the next session to cover the power factor of the any electrical system. So thank you and all. Thanks for watching this one.